Hello and welcome to this Solidity tutorial series where I will be going over the fundamentals of the Solidity language as well as including some best security practices to follow when developing smart contracts. Today we're just going to get started by learning how to install Hardhat, making a very simple smart contract, and then learning how to interact with that contract by using Hardhat. So let's begin by going over to the documentation page on hardhat.org. Then going to the general overview page and scrolling down just a little bit to the installation section. And we'll see here it's telling us we should create a new empty folder and then also initialize a new node project within that folder. So I'll go over to the Mac terminal I have here. I'm going to create my folder on the desktop and call it Solidity Tutorials. Then we need to change into that folder, and that's where we're going to run the npm init command. And it'll ask a series of questions. I'm going to leave these all at the default or just blank values for now. Next, I'll go back to the Hardhat documentation and copy this command that's going to install Hardhat as a dev dependency within our project. While that's installing, I'll go ahead and copy one more command here that's going to be used to initialize Hardhat. Again, it'll ask a few questions. So for this first one, I'm going to choose JavaScript, leave the project root at the default suggested value, include the git ignore, and definitely I want to include the Hardhat toolbox as well. So this will take a moment to install, and then once this finishes, I'll go ahead to VS Code and then open up the project we just made. I should mention that VS Code does include an extension for Hardhat, so that's pretty useful. But feel free to use, of course, whatever IDE you prefer. So let me go over to VS Code now and get that project opened up. And then once it's open, let's just take a quick moment to get familiar with the default project structure here. So first thing is that Hardhat actually created this Hardhat config file for us here and specified this version of the Hardhat, of the Solidity compiler to use for the project. So I'll just leave this the way it is. In case we did want to use multiple versions of the Solidity compiler, then we would just include a compiler's object right here, and then it'll be an array of objects where each object is specifying the version of the compiler. But for now, we'll keep things simple and just use this version that's already included here. And we'll come back to this file periodically throughout this tutorial series, because it allows us to add configurations to interact with the various test nets. If we want to add a configuration to interact with the mainnet, we would do that here as well. And what's really cool is we can add a configuration here that would allow us to actually fork our own local copy of the mainnet. So in other words, if you wanted to develop smart contracts and already be testing and seeing how they interact with live contracts, even while you're in development mode, then you can add a configuration here to actually fork your own copy of the mainnet to do that. Moving on though, we see that we have these two folders here, contracts and tests. So it's pretty self-explanatory. The contracts folder is where our Solidity smart contracts will be, and this test folder is where we're going to write our unit tests, which will be how we interact with those contracts locally. And Hardhat actually included one contract for us here by default. It's like a sample implementation of a time lock contract. And time lock contracts are very standard and common to see within DeFi protocols that have some sort of governance or community, because it's a way of queuing transactions to be executed at a later time. So for example, if you have a governance that's voted on some sort of action to be enacted on behalf of the protocol, the time lock would queue that transaction to be executed at a later point in time. So therefore, if the transaction would have been malicious or detrimental to the protocol, there's still time for the governance or some privileged address to come along and cancel that transaction before it gets executed. So that's a little beyond the scope of this video though, so I'm actually going to get rid of all this code we have here in this file, and then we'll use the same file for our contract. We're just going to rename it to counter, and we'll be making a very simple contract today that has a counter variable, then just increments that counter by means of calling a function. So every Solidity contract needs to specify the version of Solidity that it's going to be compiled to by using the pragma keyword. As you can see, the VS Code autocomplete also gave me this comment here that holds the license identifier. So these are two things that you'll see in every smart contract. I'm going to change this to MIT, and then I'm just going to put the same version of Solidity that we had in our config file, which is 0.8.24. Next, I'll define the contract by using the contract keyword and giving it the name counter. It's going to hold one state variable. It's going to be of type uint and have public visibility, and also I'm going to call it counter. So let me quickly explain what's happening in this statement right here, though. So first of all, we have a variable here of type uint. Uint means unsigned integer, so it cannot hold a negative sign, and therefore uint will always be a positive value. There's different sizes you can have for integers in Solidity, ranging all the way from 8 bits to 256 bits. However, if you just leave it as uint, that's actually an alias for uint 256. So if you do this, or just leave it like this, there's actually no difference there. The next thing is the visibility of public. So that's saying that the contract we're declaring this variable in can have access to it and both read and write to this variable here, as well as any contracts that inherit from this contract. And also any other contract on the blockchain could also access the value of this variable as well. Also, it looks like the variable is uninitialized at this point, but in Solidity, all variables are initialized to a default value if you don't explicitly set a value when you're declaring them. So for example, if I were to add this, it would be absolutely no different than just leaving it the way it was, because all integers in Solidity have a default value of 0 if you don't explicitly set that value. Okay, so next, let's go ahead and add a constructor where we're going to just pass in a value for the counter when we deploy the contract. So I'm going to again put uint here, underscore counter, and then set the counter variable to be equal to the underscore counter parameter. So the underscore is just to avoid variable shadowing, which means you don't want any sort of parameter for a constructor or some function to share the same name as the actual state variable. So we avoid that variable shadowing by just using underscores in the parameters. Next, I'll go ahead and make the function that's going to increment the counter. So we use the function keyword, give the function a name, increment. We don't need any parameters, leave the parentheses empty. And then we also want to put a visibility modifier here. So I'm going to put external, which means that this function cannot be called within this contract, but it could be called from outside the contract, which is all we need. So when we get into the topic of gas optimizations later on at some point, we'll see that using external is actually somewhat cheaper than just specifying the visibility as being public. All we got to do in this function is essentially add 1 to the counter. So we'll do counter plus equals 1. And then if you come from any background in some other object-oriented programming language, you're probably already noticing the similarities that you have in contracts and classes. So contracts are somewhat similar to classes in the sense that you have state variables, you have an optional constructor, you can have functions, and also local variables within those functions. Also, you have the inheritance in contracts as well. We'll get into that more at a later point in time. But for now, this is all we need in this contract, so I'm going to go ahead and save it. And then navigate over to the unit tests. Again, we don't need any of this for now, so I'm going to erase all of this. And we're going to add this describe to be describing our counter, basically changing that to describe counter contract. And just for consistency, let me just rename this to be counter also. Next, we're going to use ethers.js, and more specifically, we're going to use the Hardhat plugin for ethers to declare a contract factory. I should mention also that Hardhat uses Mocha unit tests. So within these Mocha unit tests, you have an optional before all hook, which you can use to set up, what you need to set up for all your other unit tests that'll follow afterwards. So first, actually, before I make the contract factory, I'm going to make a variable here that's going to hold a reference to our contract once we deploy it. So I'm going to say let counter contract. Then I'm going to define our before all hook by passing in this function here. And I need to make it async because anytime you interact with a blockchain, it's going to be asynchronous. So if you want to do things sequentially, you'll need to follow the async await pattern here in JavaScript. So next I can go ahead and make that contract factory though. So I'll say const counter contract factory is equal to ethers.getContractFactory. So this is a method that the Hardhat plugin superimposes on top of the ethers library that allows us to just pass in a contract name. And what it's doing is essentially it's grabbing the contract information, or more specifically, the contract ABI. So then that allows it to deploy this contract, and you can make copies of the contract and deploy it as many times as you want. But we're just going to deploy it one time. But first, let me quickly just touch on what an ABI is. So an ABI is a JSON set of instructions that'll tell some third-party library such as ethers how to interact with that contract, or what variables it includes, what functions it includes, etc. So we don't have an ABI right now because we didn't compile our contract yet. But if I go to the terminal here and do npx hardhat compile, we're going to see an artifacts folder appear up here. Then within the contracts folder, we'll see counter.json. So that's the ABI that matches our Solidity contract. So if we just take a quick look at it, we'll see it has some JSON information regarding the constructor, the parameters, different state variables and other functions that we have in this contract, as well as the bytecode. So we don't need to interact with this whatsoever directly, but just so you know, that's what's happening here under the hood. It's basically getting a reference set of ABI, and that allows us to then deploy the contract, and ethers will then hold a reference to the contract and know how to interact with that contract. So we can just simply do counter contract equals await counter contract factory dot deploy. And because our contract has a constructor with a parameter, we need to pass in that parameter here to deploy. So we're going to set our counter to be 1. So essentially, we're just saying, okay, we're going to pass 1 for this value here. And another cool thing I forgot to mention about Hardhat is that you can actually have console logs. So there's no native console logging in Solidity, but with Hardhat, we can import this module, Hardhat console.sol, and that will allow us to add console logs in our contract for debugging. So let's go ahead and just for fun add a console log here that's going to say what the counter value was initialized to when we deployed the contract. Okay, next I'll go back to the counter contract. Just noticed here also I forgot an await statement. That's why the autocomplete added these parentheses for me here. We don't need those actually though. Okay, so now we have the contract factory reference, and also we're now setting this variable to be pointing to a deployed version of the counter contract. Now just for fun also, let's do some logging here. Let's actually make a reference to the address of our deployed contract by doing counter contract.get address. And then maybe just to make sure everything went smoothly here, let's do an expect statement. Oops. Where we're going to expect the address is equal to the same length that you would expect for any Ethereum address. So Ethereum addresses are 20 bytes long, and they're stored in a hexadecimal string. So So 1 byte is basically 32 bits, and hexadecimal values, each character holds 16, up to 16, base 16 in other words. So we need 2 hexadecimal characters to be equal to 1 byte. Therefore, the 20 byte length will actually mean it's going to be 40 characters long. And then Solidity, you always add a leading 0x before each address, so that'll make the total characters 42. So as long as our address is a valid string and of length 42, this test should pass right here. Next, let's do one unit test, where we're going to increment the counter by 1. And then here we're going to, on our contract reference, we're going to call the increment method. We don't need to pass in any parameters here, but again, I should add the await statement. Next, let's go ahead and get value of counter. I think I forgot to mention earlier that whenever you do a public variable, it's actually creating a getter method under the hood. So all we have to do to get this value is actually just on the contract do .counter and then add parentheses, because the getter method will share the same name as the variable itself, and use add parentheses to make it into a function call. So let me just go ahead and say counter is equal to the return value from that getter. Once again, maybe let's just log it out so I can see what it is. Okay, and then let's say we're expecting it to be 2. Okay, just a quick recap what's going on here. We are getting a reference to the contract factory. Then we're assigning a reference to the deployed version of a contract to this value here, to counter contract. Then we're checking the address, making sure it's a valid string of length 42. Then we're incrementing our counter variable by 1 by calling this method here, getting the value from the getter function. Then we're going to print it out and make sure it's equal to 2. So here I'll run the npx hardhat test, and then let's see what happens. Okay, something failed here. So again, I forgot the await statement. So every single time you interact with the blockchain has to always use the await statement if you want to be able to access that value immediately and have things be sequential. So hopefully if I run this one more time, it's going to pass the tests this time. Let's see what happens. Oh, and same thing actually for this address. Alright, one more time. So now we have the await before every single statement that's calling a method on the contract. So let's try this one more time. Okay, there we go. Now we have what we expected, which is the counter is initialized to 1. That's being printed out directly from our contract code. And then here it's telling us the counter is equal to 2n. So what the n it means is basically that's a big number. So the ethers library doesn't use the JavaScript native numbers. It uses a special class called big numbers. That's because in Solidity and Solidities in Ethereum, there's no such thing as a decimal or fractional number. So you end up with really, really large numbers, more than JavaScript could safely handle. So therefore, that's why Solidity will use its own class called big number. And then whenever you see an n after number, that means it's of type big number. In case you wanted to use big numbers just in the code itself, then you would say like, let x equal n plus 100n plus 1n or something. That would be declaring these as big numbers as well. There's also a constructor you can use for big numbers and so forth, but we'll be covering more about that actually in a future video as well. But for now, everything seemed to work as intended, and that concludes this first video, and I hope to catch you guys in the next one. Thank you.